Welcome to today's Explainer. Today, we're going to demystify altimetry, atmospheric pressure, and the absolutely crucial math that keeps airplanes from hitting the ground. If you've ever looked at a flight deck and wondered how pilots navigate that invisible ocean of air above our heads so safely, well, you're in the exact right place. We're going to unpack barometric pressure, dive deep into Q codes like QNH and QFE, and learn exactly how pilots calculate altimeter errors to avoid disaster in extreme weather.
So let's just dive right into this question, because an altimeter doesn't measure distance with a tape measure, and it doesn't bounce a laser off the ground. It actually measures invisible, static atmospheric pressure. Think of it like weighing the air directly above the aircraft. As you climb, there's literally less air pressing down on you, right? So the pressure drops. The altimeter is essentially just a highly calibrated barometer that translates that changing air pressure into an altitude reading in feet.
Here is our flight plan for today. 1. How altimeters measure altitude. 2. The Q codes, QNH, QFE, QND. 3. Transition altitude and level. 4. Cold weather altimeter errors. And 5. Calculating safe altitude corrections.
Let's start with Section 1, how altimeters measure altitude. To really get how this instrument works, we first have to understand the baseline rules of the sky that it relies on. See, the altimeter assumes the world perfectly matches something called the International Standard Atmosphere, or ISA. It's basically a mathematical model that gives us a common reference for temperature and pressure. But as we all know from just looking out the window, weather is rarely standard. The atmosphere is this chaotic, dynamic fluid, yet for an altimeter to actually give us a reading, it has to base its logic on this idealized, perfect world.
Now check this out, because these three specific date points form the absolute foundation of your altimeter's brain. In this perfect ISA world, the sea level pressure is exactly 1013.25 hectopascals. The temperature down at sea level is a pleasant 15 degrees Celsius, and as you climb, the temperature drops by a highly predictable 2 degrees Celsius for every 1,000 feet you go up. We call that specific drop the temperature lapse rate. Every single barometric altimeter in the world is calibrated to this exact table.
Moving on to Section 2, the Q codes, QNH, QFE, QNE.
All right, physics lesson over. Let's step into the cockpit on the runway and set up our altimeter using something called Q codes. These are just standard universal pressure settings used by pilots and air traffic control all over the globe. The absolutely crucial point here is knowing the difference between QNH, which is the local station pressure reduced to mean sea level, and QFE, which is measured exactly at the aerodrome datum level. If you set QNH while you're sitting on the runway, your altimeter will tell you the airport's official elevation above sea level. But if you set QFE, your altimeter will actually read a perfect 0.
In commercial flying, you are going to use QNH almost exclusively for takeoff and landing. Why? Because terrain and mountains on aviation maps are measured above mean sea level, and QNH ensures you safely clear those obstacles. QFE, on the other hand, is mostly reserved for military aerobatics or specific closed-circuit training, where reading a true 0 on the runway is critical for maneuvers. And finally, we've got QNE. That's the standard setting of 1103.25 hectopascals, which you use when you're way up high flying in standard flight levels.
If you take away just one rule of thumb for pressure conversion at low altitudes from this explainer, remember this number: 30 feet. A 1 hectopascal change in pressure equals about 30 feet in altitude change. So, imagine an aircraft lands at an airport but accidentally leaves a standard setting of 1013 on their altimeter. If the actual local QNH is 993, that's a 20 hectopascal difference. Multiply 20 by 30 feet, and suddenly that altimeter is off by a massive 600 feet. You can see how that could be a real problem.
Section 3. Transition altitude and level.
So let's move into our climb phase and see how this all builds into actual airspace coordination. We know how to set the altimeter on the ground, but what happens when we leave the local area? Well, here is how pilots manage the climb. Step 1. You take off using the local QNH to make absolutely sure you avoid any nearby hills, antennas, or towers. Step 2. You climb until you hit a specific height designated for that airspace, known as the transition altitude. Step 3. Once you're safely above the terrain, the pilot reaches over and switches the altimeter from the local QNH to that universal QNE standard of 1013.25 hectopascals.
The real brilliance of this procedure is all about traffic management. By making sure every single aircraft in the upper airspace uses the exact same pressure datum of 1013.25, air traffic control can ensure perfect vertical separation.
Even if the local sea level pressure is wildly fluctuating in a massive thunderstorm below them, all the planes up high are referencing the exact same baseline. Their true height might not be perfect, but their separation from one another is absolutely flawless, which prevents mid-air collisions.
Which brings us to Section 4, Cold Weather Altimeter Errors. Okay, picture this. Our flight has crossed the country and is now descending into mountainous terrain in the dead of winter. And suddenly, we run into a major physics problem. Remember that international standard atmosphere we talked about earlier? Well, the altimeter is a flawed instrument in that it assumes temperatures are always perfectly standard. But when temperatures plummet way below the ISA standard, like in a blizzard, the atmosphere literally contracts and the instrument effectively starts to lie to you.
This comparison brilliantly illustrates our problem. Look at the hot, less dense air on the left. Pressure decreases slower, so you might actually be slightly higher than you think. But in the cold air on the right, the true altitude of the aircraft dips dangerously below the altimeter's indicated altitude. Because cold air is denser, the pressure decreases much faster with height.
This is a massive, massive hazard during instrument approaches in winter. Your altimeter might happily tell you that you are at 3,000 feet, safely above the jagged rocks below. But because the cold air has compressed those pressure levels, your true altitude could actually be 2,500 feet. If you blindly follow the altimeter in these conditions, you could suffer what the industry calls controlled flight into terrain, or CFIT.
There's a classic aviation adage that perfectly sums up this danger. High to low, or hot to cold, look out below. It hits the nail on the head. And it's exactly why you must manually calculate temperature corrections when flying into a cold temperature-restricted airport. You literally cannot just trust the dial on the dashboard. You have to do the math. And that leads us right into Section 5, Calculating Safe Altitude Corrections.
So how do we actually fix this dangerous air before we hit a mountain? Let's break down the math because it's super important. The golden rule of thumb for temperature correction is the number 4. For every single degree Celsius the surface temperature is below the ISA standard, your true altitude is off by 4 feet per 1,000 feet of height above the reporting station. I know it sounds a bit like a word problem from high school physics, but it is remarkably simple to apply when you're in the cockpit.
While transport authorities do have these incredibly complex, iterative formulas published in their manuals, this simplified 3-step calculation gives pilots a highly accurate adjustment to keep them safe. Step 1, figure out how much colder it is than standard. Step 2, find out exactly how high you are above the airport. Step 3, multiply 4/10 by your height in thousands by that temperature deviation. Let's look at a real-world example from our sources to see this in action.
Okay, imagine an airport sitting at an elevation of 3,206 feet. The published minimum altitude on the approach chart is 6,200 feet. That means your actual height above the station is roughly 3,000 feet, or 2.994 to be exact. Let's say it's freezing outside, 20.6 degrees Celsius colder than standard. We just plug those numbers into our formula. 4 times 2.994 times 20.6. The result is a positive correction of 247 feet. In this specific scenario, a 247-foot correction might literally mean the difference between safely clearing a snowy ridgeline and absolute disaster. It just proves how vital this altimetry math really is.
And here is where pilots have to be incredibly disciplined. The absolute most crucial takeaway here is that you never, ever manually dial this correction into the altimeter setting itself. Your QNH stays exactly as air traffic control gave it to you. Instead, you add those 247 feet to your published minimum approach altitude on your chart. So instead of flying down to 6,200 feet, you treat your new hard floor as 6,447 feet, and you fly that higher number on your altimeter.
It's a pretty sobering thought, right? When visibility drops to 0 and ice is forming on the windshield, knowing the hidden mechanics behind atmospheric pressure, really understanding your Q codes, and trusting your temperature correction calculations is what gets everyone on board home safely. I hope this explainer has given you a profound respect for the invisible mechanics of flight safety and the incredible workload that pilots manage to keep us all safe up there in the skies. Until next time, keep looking up.